Alright guys, I'm going to try to cover all of the reinforcement learning that you've learned so far this semester in very little time. So if after this you have a class you can go, I'm probably going to stay and continue through the slides. If you can do that, it will probably be worthwhile. So there are several forms of reinforcement learning. We're going to start with passive model-based reinforcement learning. So for reinforcement learning, or on a slide, you were given the model, and you were asked to solve, to calculate the value function, or to calculate the policy. In our case, we aren't given the model. But what if we still want to be able to learn the value functions of a given world, of given states? Well, it's possible to do that. And one way is using model-based learning. So in this version, you're going to try to learn the model, or you'll learn an estimate of the model, and then you'll use all of those algorithms that Anaka just showed you to do exactly the same thing and calculate the value function. So we start out by observing an agent acting with some policy pi. So you're watching somebody who already has a policy. And what you observe are sample trajectories that look like this, where you have state, action, reward from the first state to the last. Now, to get an estimate of the model, you're going to calculate the maximum likelihood of the transition function and the reward function. Now, you might be wondering, what is the maximum likelihood? You might not have even used that term when you learned it. All maximum likelihood is, in this case, for the transition function, it's the likelihood of, the maximum likelihood of the probability of being in state S, taking action A, and transitioning to S prime, which can be calculated by the number of times that you were in state S, took action A, and landed in state prime, over the total number of times that you were in state S and took action A. That will give you a probability for SA S prime. And then we generally assume that the reward function is very easy to learn, because we literally see, what's wrong here? We see that we get the rewards directly from our sample trajectories. So we generally assume that this is pretty easy to get. And we then evaluate the policy pi by calculating the value function using value iteration, policy iteration, or whatever you would like. It's also possible at this point, once you've evaluated the policy and gotten some v pi of s, that you could also then improve, you could create a new policy and improve it over the policy that was being followed by whoever was acting in the world and giving you these trajectories. But in this case, we get the value function, but that doesn't actually allow us to actively act in the world and to improve our policy. So another thing that we can do is active model-based learning, which is going to start the same way. We're going to, except in the last problem, we were observing somebody who was following some policy. In this case, we're going to start acting in a world following some random policy. And we'll again do maximum likelihood to get an estimate of the transition function and the reward function. And we'll again calculate V star for the estimated model. But now we're going to use the values that we get there to generate a greedy policy pi, a new policy. Better than the one that we started with, which was just acting randomly. Now, we're going to get new traces. We're going to start using our new policy in this world, except we're going to act on it epsilon greedily, which means that 1 minus epsilon percent of the time, we're going to exploit what we already know by using what our policy pi tells us. But for an epsilon amount of time, we're going to again just act randomly. And this is going to give us the exploration and exploitation that we need. That should be exploration. So and now we'll update the model, also including the new traces that we've gotten using our better policy. And when we have those new traces, the new estimates, we can then calculate a new V star, and we can repeat this process. until our model becomes as accurate as we would like. Now, I kind of waved my hand at the exploration and exploitation here. So you might be wondering, why would we want to start acting randomly when we already have a policy that is a greedy policy? It should be good. And I'll get to that with a question. So imagine that I'm giving you a job. And instead of giving you a paycheck at the end of every week, I tell you that at the end of each week, you're going to come into my office and I'm going to have you open one of two doors. Whatever value is behind the door that you open is going to be the amount of money that you get for that week's work of work. So let's say after your first week, you go in, you open door A. You get a value of 2. You get $2 for working that week. Great. And you're like, well, that kind of sucks. So the next week, you go in and you're like, well, this time I'm opening door B. I know nothing about it. Well, door B gives you a value of 1. If you were to act greedily, based on the values that you know here, you're going to open door A every time, because it gave you double the amount that door B did. And so you would do this, you have some values, you act greedily, and now door A is the door you're going to open every week. You're making $2 a week. But what if, instead of just acting greedily, we also continue to explore for some percentage of the time? So again, you go in, you open door A, now you get a value of 3. Okay, so it's not the same value every time. The fourth week you go in, you open door B, you get $1 million for that week. So clearly, there's some value in continuing to explore the state space. Now let's say maybe door A only gives you values 2 or 3 with equal probability. Maybe door B gives you values between 1 and 1 million with equal probability for each value. That's something that you would eventually learn, and as you learned it, you would start decreasing the amount that you open door A, and increasing the amount that you actually do, which is going to start leading towards door B. That's going to converge to an optimal policy. So, that was model-based learning, where you didn't have a model, but you learned it. It's also possible to learn without coming up with a model at all. And we start out with the naive case of the Monte Carlo method. Also, you guys called it the direct policy evaluation. So, in this case, again, you're given a policy. This is going to be passive learning, where you're just watching somebody act in the world. You have some policy, and this policy shows if you're in state B, you go right, state C, you go up, state E, you go up. And if you're in states A or D, the only action that you have, which is related to your question, is to transition from A to X or D to X. So this is, of course, going to be in your policy because it's the only action that's possible in the world. So with Monte Carlo learning, you'll again learn from a series of episodes. So we have one where we go from E to C to X, or E to C to A, B to C to A. And you'll observe these episodes using the policy. And then you're going to calculate V of S using the average return from state S to the end of the episode for every time that you saw state S. So if you're in one place and in one episode you see state S, and from S to the end you got a reward of 10, and in the next episode you also saw state S, and between S and the end you got a return of 20, then V of S for those two observations is going to end up being 15. It'll be the sum of the returns from S to the end of the episodes over the total number of times that you saw state S. So, to calculate V of A, using our 4 samples, our 4 trajectories through space, we see A 3 times, here, here, and here. So we add up the total return from state A, which is 10 for each, and divide it by the total number of times that we saw it. There's 10. Same thing for B. We see B twice, and from B we see -1, -1, and 10, so that'll be 8. And we also see -1, -1, and -10, so that'll be -12. We sum them up, we divide it by the total number of times that we saw B, and we get our value estimate for B. We'll do the same thing for each other one. And I guess let's take a look at C here. Notice we see C 4 times, but C starts in the middle of the transitions, which means that the first return for the value of C in this sample is going to be -1 plus 10. Not -1 plus -1 plus 10, -1 plus 10, because we started at C. So you do the same thing for each of the episodes, and you get the values for each of them. That is the Monte Carlo method. Now there are some problems with it. Notice that states B and states E only ever went through C. So, and this is supposed to represent the values that you get for being in this state and going forward. So why is it that even though B and E both go through C, B, C, and E all have completely different values? Surely they should be similar. And that's because the Monte Carlo method doesn't exploit the Markov properties. All it does is it looks at the total return at the end of it and updates it. So because we started with B and ended up getting -10 somewhere, we got a bad value. We started at E, we got a lot of points back, we got a high value. So this means we're actually wasting a ton of information. B has no idea that he has any probability that he could get a high value for A. Also, notice that in order to do this, we have to take all of our episodes at the beginning. And after we had those episodes, we could compute the values. But if we were to get more episodes later on, we would have to recalculate our values of S for all the old episodes plus the new episodes. However, that problem can be fixed by using an iterative method. Now here, there's a lot of notation, so I'm not going to walk you through it. But the important part is this. This first line here is what we just did for the Monte Carlo simulation. This second line here is the same exact thing. We've just done some algebra. And what we've done with that algebra is we've taken an equation that requires us to have all the samples at the start to calculate the mean, and we've converted it into an incremental equation, where we're still calculating the mean value, but we can do it after each episode. And each new episode that we add in that gets a value is going to be given the right amount of weight to just compute the mean. So this is the same thing written at the bottom there, but cleaned up a little bit. And this is really important for reinforcement learning. Notice to calculate our new estimate, we're taking our current estimate plus some step size, which in this case is going to be that small sum that we need to add to calculate the actual mean, times the actual return minus the current estimate. So here we have current estimate, and actual return. Notice that what's inside of these parentheses here is the difference between the actual return that we got and what we thought we were going to get before we saw this episode. And you guys may have seen this, and actually let's take this a step further. So here we have some step size. This is us calculating the actual mean. But notice that for every value of this state, our value estimates are going to get better and better. And yet with this step size, we're going to be given each new episode's information the same amount of weight, which we don't want to do. We want to say that the new episodes, our new values, have more weight. And eventually we want to forget about those old weights because they didn't have that much information involved. So instead of calculating the actual mean, we can calculate a rolling mean by just replacing that 1 over the number of times we visited state S with alpha, some value between 0 and 1. And you may have seen this equation as one that's like 1 minus alpha times v of st plus alpha times something else. If you were to multiply this out, again, do some algebra, you'd realize that this is the exact same equation. They both do the same thing, but the notations kind of give you intuition behind what they can mean. So as a learning exercise, I'd advise you to do the math and then think about what does this mean? Taking our value and then adding a small amount towards the difference between the equation that you were shown in class. Yes?
You need to indicate that alpha is actually bound between 0 and 1.
Yes. Yep. Yeah, that's correct. So alpha here is a value between 0 and 1, so small step size. And this just tells you the same thing as the last slide. Okay, so that was Monte Carlo learning. And we said that a problem with it is that it didn't utilize all the information that we had, and until we got the incremental version, we also had to have all of the episodes at once. Well, in both of those versions, the incremental and the non-incremental, we had to have a projection, a sample. So at some point it had to end. But what if we're in an online world that doesn't have an ending state? It just keeps going. We couldn't use Monte Carlo. Well, all of these problems can be resolved using temporal difference learning. You guys learned it as temporal difference learning. That technically includes TD0 and Q learning. Q learning is a temporal difference learning algorithm. But so when I say TD0, I mean the temporal difference learning that you were taught. So with this, we can take advantage of the Markov properties. So now we're not wasting information. And all we have to do is take the equation that we just had there for our incremental Monte Carlo method and replace it with this value. So before we had G sub t, which was the return that we would expect to get, which is the actual return that we got from some state to the end of the episode. Now we're replacing it with this red text. So my question to you is, what does the red text represent? I'll give you guys a few seconds on this. All right, who thinks the red text represents the actual return from the state S? How about the actual return from the state S prime? The expected return from state S? No, all right, we have a few hands. If the rest of the class doesn't raise their hand for D, I'm going to be very upset. How about D, the expected return for state S prime? See, everybody raised their hands because you didn't want to upset me, but it turns out the actual answer is C, the expected return from state S. So what's changed here? Before, we had the actual return from state S. Now, it's the expected return from state S, where instead of using the actual return, we're taking the actual reward that we got from state S, and then we're adding some discounted value of our previous estimate. So notice now that we're coming up with a new estimate, V of S, by bootstrapping off of our previous estimate, coming up with a new estimate by bootstrapping off of our current estimate of V of S prime, which is incredible because we end up actually starting V of S with any arbitrary values that we want, and then we're able to use those guesses to actually come up with a correct answer. So, now, TD0, we are trying to find the values of each state. And we have this layout here. Now these rewards aren't actually known, but they are the rewards that they're going to get for landing in those states. So, let's say we have one Morty. And this is Morty's total life. He goes from state 1-1 to state 2-1, and then he dies. But we aren't actually waiting for this whole thing to happen. We're going to learn as Morty 1 goes through the world. So he's going to go from there to there. And we start out with V11, and this is just plugging this number into this equation. And we'll calculate that value as 0. So, this means that Morty, when he moves from state 1-1 to 2-1, the value of state 1-1 is going to now update to 0, which is what it was before. So as he leaves a state, we get more information, and the state that he just left gets updated. So if he were to not die here, and he were to end up back in state 1-1, he would now have new information about that state, even though his run through this world hasn't ended yet. So again, V21 to death, we'll do the same thing, plug the numbers into the equation, get a value, and die. So now 2-1 gets updated with -5. Well, fortunately there's a lot of Mortys. So we start with Morty 2. And Morty 2 goes through this space. I'm kind of short on time here, so I'm just going to step through these. From 1, 1 to 1, 2, the value updates to 0, so we should see the state he just left turn to 0 again. From 1, 2 to 2, 2, it's 0 again, so he's going to go up here. And then from 2, 2, he gets teleported out with a value of 5. So Morty gets teleported, and the state that he just left gets updated with the new value. Let's do one more Morty. Note here that these Mortys are all following some given policy. We don't know what that policy is, but he has a policy that he's following. And this Morty is going to do the same thing as the last one. When this episode ends, you'll notice now that V12 gets updated with a new value of 2.25. And V22 now gets updated even closer to the actual return of 22 with a value of 7.5. So you can see that even though we're now using the information that we get from each next state, it actually takes a few runs through, and we have to see each state multiple times in order for all of these values to get backed up. Because so far, we still think that 1, 1 has a value of 0. Yes?
Should the bottom right corner be 2, 1?
This is 1, 2. They're indexed by this. I tried to keep it consistent with what you guys had already seen. I'm not a fan of this indexing. All right. So, TD0 allowed us to evaluate each state without having a model of the world, but without a model, we can't use V of S to act in the world. Why is that? Well, if we have V of S, in order to decide what is the best action to do, we still have to have a model of the world in order to find out where we land, in order to follow the transition table. So how can we do model-free control? And actually, before I do that, I'd like to note that we went from the Monte Carlo method, which used the return from the end of the episode, and TD0, which is just like a single look ahead at our next estimated value. There's something called TD lambda, which averages the two of these out. And in fact, it shows that that converges to the optimal value much better. And so it ends up taking some average between the Monte Carlo method and the TD0 method. The Monte Carlo method is TD infinity. If we had TD infinity, it would be Monte Carlo. TD0 is a single step. If you get average sums between 0 and infinity, you converge faster. But that won't be in your exam. Alright, so now we want to be able to act in the world. And this should actually be active model free learn here. But we're going to need a lot more Mortys to do that. So, notice that we now have a new equation. A state action value function as opposed to just a state value function. But notice that not much has changed here. The only difference is now we're taking the max of our actions here, and we end up with our state action values instead of just our normal values. So, using Q-learning, which of the following are true? Rick can always learn the optimal policy when Mortys are following a deterministic policy. If Rick buys enough Mortys, he can let them all act randomly and still learn the optimal policy. Or Rick can let the Mortys improve their own policy by acting greedily on the learned Q values. Which of you think number 1 is true? How about number 2? And number 3? Alright. The correct is, in fact, number 2, which is that if Rick has an infinite amount of Mortys, he can just let them follow a random policy, and he will still converge to the optimal policy. But this would be expensive, because we're now in a place where we can learn how to act better, but doing this, we're not going to be utilizing that information. In the third one, where it says, well, Rick can let the Mortys improve their own policy by acting greedily on the learned Q values, this is almost true. The only stipulation to it is that instead of letting them act greedily, he would have to tell them like the greedy action that they could take most of the time, but some of the time he would still need them to jump off a cliff even if he's already seen Morty's jump off the cliff. Because maybe the seeds are only over that cliff, so you have to continue exploring. Let's look at an example. This one doesn't step through as many things, but we can see in the top left here, the solid arrows, so we already have a Q function. The solid arrows show the values for our current estimates, and the arrow shows the trajectory of a Morty through the world. In the bottom, we have the rewards that we'll end up seeing when Morty makes these transitions from one state to another state. We don't know them, but again, we'll see them when Morty takes the path. So we're asked to calculate the estimated Q values after Morty now completes this trajectory with an alpha of 0.1, so a small step size, and a gamma value of 0.5, which is our discount factor. Again, this is just plug and chug. I'm sure you guys want to get out of here. So we'll step through. We'll see that when we have 1, 1 up, we get the value of 2.2. So that value gets updated. Again, from state 2, 1, and taking the action right, plug the numbers in, and that value gets updated. It ends up being the same. And because we only saw these states and actions, those are the only state action values that will end up getting updated. So, if Morty's run with a random policy, they act randomly the entire time, that's fine. Otherwise, Morty's could act epsilon greedily on this new policy as long as they continue exploring some of the time. That's it.
I know, right?